where C is a triangular curve consisting of the line segments from 0, 0 to 1, 0, from 1, 0 to 0, 1, and from 0, 1 to coming back to the origin 0, 0. So number one, let's sketch the region, of course. So let's sketch the region of integration, and in this case we want to go from the point 0, 0 to the point 1, 0, and then from the point 1, 0 to the point 0, 1, and then to the point to the origin back again. All right? So that's essentially C1, C2, and C3. But well, we're not going to parameterize anything. We're going to use Green's theorem in this case. And all we have to do to evaluate this line integral, so just go, okay, let's just write the equivalent. So that's the cyclic, the closed integral, f dotted with dr. And well, instead of parameterizing anything, we will evaluate this double integral over r of the partial g with respect x minus the partial of f with respect y dA. Okay? And well, so we need to take the partial derivatives. Where do we get those from? Well, so in this case, this is our f, and this is our g. So f equals x to the fourth, and g equals xy. That means partial of f with respect y. That's going to be that's actually 0. All right, and partial of g with respect x, that's y. And we will evaluate this integral right here. So let's replace the corresponding partials. So that's the double integral dg dx, that's y, minus 0 dA over r. And that's in this case, that's y dA. And well, in this case, well, let me actually get rid of the r. Well, okay, that's fine. So let's put the limits of integration. And in this case, well, here is where we decide the order of integration. Well, this is going to take us back to double integrals, in which we will decide whether this region is vertically simple or horizontally simple. And in this case, it happens that it's both vertically simple and horizontally simple. And we usually work, well, I do the vertically simple because I would integrate with respect to y and then with respect x. That is in backwards alphabetic order. So, but I mean, if you want to do it the other way, of course, that's fine. So dy dx, well, the limits for in the y direction, well, it's top minus bottom, that is whatever the equation of that line is, and minus that horizontal line. Well, in this case, it's going to go from 0 to whatever that equation of this is, and in this case, that's the equation of the line. Okay, it has a negative slope, -1 as a slope, and it has a y-intercept at 1. And so it's going to go from 0 to negative x plus 1, and the limits in the x direction is going to go from 0 to 1. All right, so all we have to do is evaluate this double integral, and so in this case, integrate with respect y. That's the integral from 0 to 1. That's a y squared over 2, evaluated from 0 to negative x plus 1 dx. And using the fundamental theorem again, that's from 0 to 1, negative x plus 1 squared over 2 minus 0. That's simply this integral right here. And well, in this case, there's a couple of ways to evaluate that integral: by substitution or expanding the binomial and then integrating 3 terms. But well, after doing this integral, we should get a 1/6. And as you can see, it's a lot quicker to evaluate this line integral using Green's theorem. You might remember from the previous section where we cover the fundamental theorem. Well, before covering the fundamental theorem, in this case, well, How we would evaluate this integral without Green's theorem? Well, parameterizing three curves, and then evaluating three line integrals. And again, even though it's not the biggest deal in the world, it's a little tedious to do, you know. So I think that's why Green's theorem is a lot more powerful, and you'll see in the next examples how powerful it is, because, well, you'll see. All right. Let's look at another example, the closed integral of 3y minus e to the sine x dx plus 7x plus the square root of y to the 4 plus 1 dy, where c is a circle, x squared plus y squared equals to 9, that is a circle of radius 3. And, well, yes, the integral looks scary, I know. Yeah, so in fact, even if you try to integrate each term, I don't think there's a way, but you'll see what's going to happen. So we're going to use Green's theorem. So we're going to evaluate the cyclic integral, or the closed integral, by means of the double integral by Green's theorem. And that's partial of g with respect to x minus partial of f with respect to y dA. Well, so let's sketch the region of integration in this case. So it's the circle of radius 3. And, well, the partial of f with respect to y and partial g with respect to x. So even though the integral looks really scary if you wanted to do the other way, the parameterization way, well, take the partial of f with respect to y, that's just 3. And take the partial of g with respect to x, that's 7. All right? So no need to parameterize. And even if you manage to parameterize that thing, it's not going to be a good idea, to be honest, because you will have to have like sine of x, which is sine of arc cosine. It's not going to be pretty. All right. So again, lucky for us, Green's theorem, and that's g. That's a 7 minus 3 dy dx. You know what? Let me leave it like dA for now over r. So that's going to be 7 minus 3. That's the double integral of 4 dA over the region R. And, well, so we could evaluate this integral using polar coordinates, because it's a circle, and we're going from 0 to pi, all right? But check this out. I'm going to take out the 4 outside. And, okay, question. This integral that I'm highlighting without the 4, what does that represent? It's the area. Can we find the area of this circle instead of evaluating a double integral? Oh my God, right? So area equals pi r squared, area equals pi times 3 squared, which is 9 pi. Not even an integral, right? We just denoted the integral. 4 times 9 pi, result 36 pi. That's how powerful Green's theorem is. You don't even, in some cases, you don't even evaluate and just set it up. But because we know that the double integral, when there is a single, an invisible one in the integrand, just get the area. Get the area. That's it. Hmm? Yeah, I know. Because you look at the integral, it's horrible, isn't it? But once you get the partials and then you get to see the double integral, hey, hold on. So check this out. You know what that means, right? Mm-hmm. Yep. Exam question, right? That little star means exam question. Let's do another one. So we have this line integral of y minus x dx plus 2x minus y dy, where over C, where C is a circle, again, it's a circle of radius 3. It's the same circle. Oh, wait a minute. No. There's a little typo here. This, because when I copy and paste the text, C is the boundary of the region lying inside the rectangle by x going from -5 to 5 and y going from -3 to 3, and outside the square bounded by x going from -1 to 1 and y going from -1 to 1 as well. Well, number one, let's look at this region of integration. So right here. All right, so that's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And it's going up by -3 to 3. 1, 2, 3, and 1, 2, 3. So it's going to go. Let's draw that box. And inside by another rectangle, which is this one. And, well, let me shade the area that we want to find. Shade the region of integration, rather. That looks a little weird. Yeah, much better. All right. So that's the region over which we will integrate. So number one, again, let's identify f and g. So in this case, f equals y minus x and g equals 2x minus y. The partial of f with respect y, that's 1, and the partial of g with respect x equals to 2. All right? So when we set up the integral right here, that's the cyclic integral over C, or the closed integral, dotted with dr. So that's the double integral by Green's theorem. Partial g over partial g with respect x minus partial f with respect y dA. And we know this information already. That's the double integral. What's this? 2 minus 1 dA. And that's simply the double integral of dA over r. However, here is the thing. If you go back to the definition, Green's theorem is supposed to be used when we have a simple closed region. This is not a simple region because we have that hole in the middle at the center of the region. But in this case, we can still use this idea of the area because, well, we can find the area of the rectangle in green and subtract the one that we didn't shade. So this means that if the outermost rectangle goes from -5 to 5, that means this base is 10, and if it goes from -3 to 3, this height is 6. And for the inner one, that's 2 by 2, I believe, right? So all we can do is simply subtract those two areas. 10 times 6 minus 2 times 2, which is 60 minus 4, which is 56. And that's the value of the integral. Now, how we would have done this integral if we didn't know Green's theorem? It's possible. Okay, let me just give you a preview. So we can start over here. That's C1, C2, C3, C4, C5, C6 in this direction, C7, C8, C9, C10, C11, C12. Do you imagine having to parameterize 12 equations? and evaluate 12 line integrals. All that work is simplified thanks to Green's theorem. Just find the area. Yes?
So is the only reason it worked with just the areas because the actual function you're integrating turned out to be 1? So you see how you did the partial of g in terms of and then the partial of f in terms of y and ended up being 1?
Yes, and even if we had another difference like we did, that's a good question, like we got in the previous example, we had a 4. It was this area times 4. And over here, it's the value of the area. So ultimately, what are we calculating anyway? So we are calculating the work done by the particle to go along the edges here, which is these 12 different paths I traced individually. But instead of finding 12 parameterizations and evaluating 12 line integrals, just find the area. Well, if it happens to be one shape that we know for sure, then we can get it. But otherwise, just evaluate the double integral in like example number 3, in which we had to evaluate the integral because it wasn't really like the most known shape. All right. Okay. So all right. So again, one of the consequences for Green's theorem. So what is this useful for? So notice how in this case we were using Green's theorem to evaluate a line integral in an easier way without having to parameterizing, or without even having to find a potential function, which either way can take its own work. We can use this theorem backwards. We can use the line integral to find area. And well, so here is the thing. Notice this part of the integrand right here. So if we look, okay, let me write the whole formula again. Okay. So if we have the closed integral, the cyclic integral, f dr, so this is equal to the double integral of r over r of the partial of g with respect x minus the partial of f with respect to y dA. However, this integral, this would be a special integral if this quantity, the difference of the partials, equals to 1, and we know what the value of that integral is. It's the area. All right, that will give us the area. Now, our job is to transform, look for different functions in terms of some functions f and g that produce a -1 when we get these partial derivatives. And well, although there's many options, many choices of functions, the easiest choices are to take f to be equals -y/2 and g equals x/2. All right. So if we take the partial of f with respect to y, that's -1/2. And if we take the partial of g with respect to x, that equals to 1/2. And now applying the double integral in this case, we using Green's theorem. That's well, let me use the compact notation. So no, that's a g with respect to x minus f with respect to y dA. That equals the integral over c of f dr. So we're going to use this theorem backwards this time. And this is the same as saying in differential form the integral of -y/2 dx plus x/2 dy. So we would be evaluating that line integral in order to get the area. So now we're going to use the other side of of Green's theorem in this case, the formula for Green's theorem. And to make this more formal, well, notice in this case we can factor out. I'm going to factor out the negative, the 1/2. I'm going to factor the 1/2. That's a 1/2 integral over c of x dy and minus y dx. Okay, is that what I have? Well, I'm just changing the signs over here. And let's formalize this using this theorem. So if R is a plane region bounded by a piecewise smooth simple closed curve oriented counterclockwise, the area R is given by this line integral. So we will this time we will have to parameterize. We will do some parametric equations and evaluate the line integral in parametric form, but this time we're going to use that idea to find the area, because since we did the opposite, use the area integral or its multiple to find the work done by the particle, which is the line integral. Now let's do this backwards. And why do we do that? Well, so I mean, it seems like we already know enough about finding areas of shapes. I mean, area of a circle, pi r squared, area of a rectangle, length times width, area of a square, length of the side square, you know, so we already know those formulas. But what about a formula to find the area of the ellipse? Have you ever thought of that one? I mean, it's quasi-circular, but it's not a circle, right? Actually, it's the circle. It's basically the special case of an ellipse in which, well, all the distances from the center are equidistant. You know, well, that's the definition. But it's not the same for the ellipse, and that's what's next. That's we're going to apply that to find an area, a formula for the area of the ellipse, given by x squared over a squared plus y squared over b squared equals to 1. So, how are we going to go about this one? Well, so number one, well, let's sketch the region. So let's sketch the ellipse. And well, we don't know which one is bigger, whether it's A or B, but it doesn't matter. I'm going to assume that A is the largest, is larger than B, and I'm going to draw the ellipse in the following way. It's going to go from negative A to A, and from negative B to B. Recall that in this case, the B number is the length of is related to the length of the minor axis, while the A number is related to the length of the major axis, right? So how we're gonna well, we need to parameterize this in order to evaluate this integral. Well, parameterize. And well, that's going to take us back to Calc 2 when we parameterize ellipses. And it's very similar to parameterizing a circle, x and y. So back when we parameterize a circle, we call this r cosine theta, and or did I use? Oh, let me use t instead, and r sine t. But in this case, well, this is not a circle, so we're not talking about radius. Actually, there is a minor radius and there is a major radius, so we need to find something else. So how about for x, we use a cosine t and b sine t, which is in this case the coefficients a and b are related to the lengths of the major and minor axis, respectively. Well, so let's write this this set of equations. This set of equations as a vector valued function. So r of t, r of t equals, using component form, that's a cosine t comma b sine t. And let's find the derivative because, well, we need to find the derivative to evaluate an integral. So r prime, that's negative a sine t b cosine t. All right? So that's all we need to evaluate a line integral. And well, in this case, so what do we need? So area, which is in this case by means of a line integral, 1/2 the cyclic integral over c of x dy plus, minus y dx, where x, what's our x in this case? Our x is a cosine t. And dy, well, dy in this case is b. So this is, if this is our derivative, this is our dx, and this is our dy, all right? Because that's the x component and the y component. So x dy, so we multiply this by b cosine t, and then minus, make some room over here, all right? Minus, what's that? Y, which is b sine t, and dx, which is negative a sine t, and the whole thing multiplied with dt. And well, so in this case, what we're going to do, so actually I'm going to change this symbol and integrate between 0 and 2 pi. And the limit 0 and 2 pi makes sense because, well, we're going around, we're going one cycle, right? So let's simplify this. So what are we going to get? We're going to get 1/2 the integral from 0 to 2 pi of ab cosine squared t, and the negative times the negative, that's plus, that's also ab sine squared t dt. If we factor out the ab, or we can actually take it out of the integral because those are constants. So that's 1/2 integral, 1/2 ab integral from 0 to 2 pi of cosine squared t plus sine squared t dt. And well, that's an identity that equals to 1. 0 to 2 pi dt, and the integral of dt, that's, I'm missing the a and b, 1/2 ab t from 0 to 2 pi, and that's 1/2 ab 2 pi minus 0, which is simply ab pi. And that's a formula to get the area inside of an ellipse. I mean, let's make sense out of it and compare it with the area of the circle. You know, the area of a circle, pi r squared, right? And well, that's the same as saying somehow pi equals r times r, where it looks sort of like this a and b, because this is the minor radius and this is the major radius. So it's the product of the minor and the major radius times pi. And if you did it the same way with the circle, major radius, minor radius, well, in this case it's the same radius, so that's r squared, right? So when I first saw this formula, it was actually because of Green's theorem. I never saw this formula before until I got into this, and I saw it, and I was like, oh yeah, makes sense. It's pretty cool, right? And let's see what's next.